off. All right. Hello, hello, hello. How is everybody doing?
Doing good.
Awesome. Awesome. Now I've got my Mac computer back, so I have a background now and hopefully won't have nearly the technical issues that I was having. So feel a little bit more back in the saddle today. So let's get started. So here is today's warm-up question, and it's a little bit different than previous warm-up questions that I've asked. This question is more of a check-in. One thing I love to do a few times a semester is just check in, see how you're doing, not just in the class, but in general. So here's the link to that. And one of the things I really want to urge you as you fill this out is only share what you're comfortable with. But it's just a personal check-in. How are you doing? How are things going with, obviously there's a lot going on. Now that we're past Labor Day, we're kind of at this place where the semester really kind of starts to show its teeth a little bit as assignments start coming due, midterms come up, and now that we're past Labor Day, it's like summer is kind of like finally over. And so just as we kind of transition into this more like fall season and so on, just how are you doing? So I'll paste that link again as people sign on. I'll give you a few minutes to answer this, and then once I see that most people have answered it, we'll talk about it really quickly. One thing I will say is I will not share the answers the way that I normally do, so I won't actually put them up on the screen, just to kind of respect the privacy of people if they share anything personal. But I will kind of look over them and kind of say, okay, so this is how it looks like people are doing. So yeah, so just take a few minutes, write your thoughts down, and then we'll jump in. Okay. So, and as always, as more people come in, I'll paste the link a few more times. Okay. And looks like a few more people have come in. Let me paste that link again. Alrighty. Let's take one more minute. Looks like most people have started to respond. Mhm. Mhm. All right. I'll paste that link again if anybody else needs it, but it looks like most people have responded. As always, if you're still writing, not a problem. But let's see what people had to say so far. So there's definitely a lot in here about the fact that, yeah, the semester is really starting to ramp up. We're really kind of getting to that point where things are coming due. There's definitely some performance anxiety related to quizzes and so on. Um, a lot of people are also talking about how they kind of feel transitioning back into more in-person learning, more in-person environments. Um, and I'll actually say, just from a faculty perspective, there's definitely a big push from administration to really start resuming kind of a lot of the in-person stuff. Um, and yet at the same time, I think there's also definitely a very cautious move forward given the most recent surge in the Delta variant and everything. It definitely kind of feels like a very weird time. And in fact, I would say, except for the very beginning of the pandemic, this is kind of the weirdest time in all of this, is we're kind of still trying to figure out what's happening now, like what's next. Um, but that definitely does create a lot of anxiety. Um, I would say there's about a 50-50, at least from what I'm looking at here. There's about a 50-50 sense in terms of many people are feeling like they're doing just fine, things are going smoothly, they've gotten the hang of things, and then the other half feel very overwhelmed, feel very worn out, feel very nervous about what's coming up. So I'm definitely kind of seeing that. Um, there's also some really cool milestones that people have shared here. Some people have gotten new jobs. Somebody got a bid for their frat, which is awesome. Um, a few people are really looking forward to the cooler weather of fall, which I have to admit, fall is, um, I'm born in spring, so I used to tell people that spring was my favorite season, but I've realized like really I'm about fall. I love fall. Um, and so there's definitely kind of that excitement that fall is coming, that it's getting cooler. We'll start to see some leaves changing colors. I'm finally getting pumpkin spice, which I love. Um, I know I'm one of those people. Um, and let's see if there's anything else really big being mentioned here. Um, so yeah, some really cool stuff that I'm seeing here. But there's definitely a lot of mental anxiety. There's definitely a big sense of like feeling overwhelmed as well. And I just want to say more than anything, if you're feeling that right now, that is completely normal. And it is perfectly okay to feel anxious right now with just everything going on. And I'm telling you all that because I've had to tell myself that too. So if you're feeling anxious, if you're feeling nervous about everything that's happening, then that's perfectly normal. And for those of you who aren't, that's good too. Um, so then the next question I ask, and I always ask this question when I do check-ins, is do you have anything that you're looking forward to? Um, and if so, what? Let's see here. The cooler weather. Yes, I'm very excited about that. Hopefully, some rain. We need it. Um, Meeting other people and making connections. Um, Getting into the frat. That's awesome. Um, Interesting new classes, experimenting and learning about networking. I look forward to every paycheck. Yep. Payday is always something to be excited about. A birthday's coming up. Um, let's see here. Holidays. A lot of people are looking forward to the holidays. Um, some people are already looking forward to winter break. I don't blame you one bit. Um, the movie night that they're having on campus in the lawn. Oh, that's pretty cool. Um, just getting through the semester. Oh, somebody's getting married next month. Congratulations. Fall weather, holidays and food with loved ones, winter break, upcoming holidays, winter break. Um, so one of the things I really want to just very quickly say, and this is something I want to urge each and every one of you to do. Um, and I know that it's not necessarily related to climate change, but it's still worth talking about. Um, if you don't have anything that you're looking forward to right now, give yourself something to look forward to. Um, it could be as simple as going to Starbucks and getting your favorite coffee, or taking half an hour and playing your favorite video game. Um, or it could be something as big as a trip, or a vacation, or a weekend away, or anything like that. Um, so it could be something big, it could be something small, but I really encourage each and every one of you. When you get bogged down in sort of all the craziness of quizzes coming up and assignments are due and all that kind of stuff, it's so helpful to have something to look forward to. It's so helpful to have yourself a little prize to keep your eyes on. Um, and I'm saying that because that's what I have to do as well. Um, and so I just want to encourage all of you, even just something small, give yourself something that you can look forward to, that you can be excited about. Um, and again, it doesn't have to be big, it doesn't have to be complex or anything like that, but it's just a way to get you motivated, just a way to get you going, and to help you kind of keep your head up when things aren't looking so good. Um, for me, I actually found out that one of my favorite comedians, who is primarily an East Coast comedian, um, and she's actually on America's Got Talent this year. I just found out that she's doing a performance in Los Angeles this weekend, and I get to go and see it. So I'm really excited about that. That's what I'm looking forward to. Um, but it's just kind of nice to have those things to look forward to be excited about. And so I just wanted to encourage all of you as we kind of start getting into the mire of this semester and as things really start to pick up, give yourself something to be excited about because it will make all the difference in the world. Okay, so that's it as far as the warm-up question is concerned. What I wanted to do though is I do have obviously some content to talk about today, but I also wanted to talk a little bit about the homework. I know some people have already finished it. Some of you probably took a look at it and thought, I can knock this out in half an hour. Others of you probably took a look at it and feel like a deer in the headlights. So what I wanted to do is take maybe 15-ish minutes or so and kind of go over the homework a little bit. So those of you who might feel kind of stuck or feel a little nervous will feel better about it. All right. So, and I usually do stuff like this in the days leading up to when the homework assignment is due. So let's jump in and talk about it real quickly. So there are 5 questions on the homework. 2 of them are purely qualitative things that you can kind of Google search or that you can sort of look up answers to or sort of come up with a pretty open-ended answer to. I'm not going to do a whole lot with those, but what I did want to do is the other questions I think kind of make people feel a little bit nervous because there's numbers and there's math and so on. And so what I thought I would do is I thought first I would take the first question and actually change the numbers a little bit and show you how to do it for those of you who haven't done it yet. Then I'll show you a little bit on how to tackle that second question. And then we'll talk about the fourth question a little bit. That's the third one that has a graph. And then we'll go from there. Okay, so for this first question, I gave you 2 pieces of information. I gave you carbon dioxide concentrations in 1958. That's when David Keeling first launched the Mauna Loa Observatory Station. And then more recent carbon dioxide data from the same location. And what I wanted you to do was to actually calculate how much carbon dioxide concentrations have changed during that time. Really quickly. Oh, that question's always such a loaded question. It is graded based on accuracy. It is graded based on accuracy. So especially the questions that have numbers because there are, but yeah, no, it's graded based on accuracy. Okay. So what I thought I would do is, so for this first question, I actually changed the numbers a little bit, gave you a slightly different scenario, but it is the exact same approach. It is the exact same approach. And so what I did was I gave you carbon dioxide concentrations for January of 2020 and for January of 2000. And what I want you to do here is I want you to calculate first off how much change has happened, and then the second thing, the second part, what is the rate of change? So here's how you actually do this. So for the first question, how much change has actually happened? I gave you 2 numbers. So this was the January 2020 number. So in January 2020, carbon dioxide concentrations were 413.37 parts per million. And then in January 2000, so 20 years earlier, the value was 369.14 parts per million. And the question I asked is, how much have carbon dioxide concentrations risen since 2000? So how much change has occurred? Well, to figure this out, all you do is you take your 2020 value, the most recent value, 413.37 parts per million, and you subtract the earlier value, 369.14 parts per million. So you're taking the more recent value and you're subtracting the older value. And that's going to give you, if I bust out my handy dandy calculator, also known as my phone. Here we go. 413.37 minus 369.14. This is what I get. Sorry if it blends into the background. So here's what this means. This means that since January of 2000, or between January of 2000 and January of 2020, carbon dioxide concentrations have gone up 44.23 parts per million. So since 2000, carbon dioxide concentrations have gone up 44.23 parts per million. So that's how much they've changed since January of 2000. So that's the first question. This is what I think many people in the world of algebra call the rise. So this is how much change has occurred. Now, the second question is, on average, how much have concentrations risen per year? Now what I'm doing is I'm calculating a rate of change, or as you may have heard about it in an algebra class, a slope. For those of you who've taken algebra before, and if you haven't, that's totally fine. But for those of you who've taken algebra before, how do you calculate a slope? How do you calculate a slope? Rise over run. Exactly. So how much has the y value changed versus how much has the x value changed? Well, in this case, our rise is 44.23 parts per million. Our run, on the other hand, that's how long this change has occurred over. Our run is 20 years. So 20 years, that's our run. So to calculate our rate of change, to calculate how much change has occurred, or how much is occurring per year on average, what we would do is we would take 44.23 parts per million and divide it by 20 years. So our rise divided by our run. 44.23 divided by 20. And that gives me 2.2115 parts per million per year. Okay. So a question that many students will ask me is, how much do I round? How much do I round? Now this class, because it's not a technical class, I usually don't spend time talking about significant figures and how much of that kind of stuff. Here's what I always tell people: round to the nearest 2 decimal places. So round to the nearest 2 decimal places. And so in doing that, you would get 2.21 parts per million per year. 2.21 parts per million per year. So here's what this means. What this means is that on average, between 2000 and 2020, on average, every year, carbon dioxide concentrations have gone up 2.21 parts per million. So for every year, we add another 2.21 parts per million. This gives us an idea of how quickly carbon dioxide concentrations are going up. So that's why we do this. It's not just busy work, it's actually to kind of give you a sense of how quickly is this change happening. So that was the first question. And really for the homework assignment, the only thing that changed, or the only thing that changes for the homework assignment is instead of doing it for between 2000 and 2020, I give you 2 other dates. But you do the exact same thing. You calculate how much has changed based on what the more recent value is and then subtracting the older value. And then whatever you get there, you divide by the number of years. And once you do that, boom, you've got it. You're all good. So that's question number 1. Okay, for question number 2, what I'll actually do is, give me 1 second here. What I'll actually do, there we go. So for question number 2, there's a figure down here that actually shows you how temperatures have changed. But there's actually something that's even a little bit more helpful. There's actually a data table that you can access by clicking on this link right here. And it takes you to this data table. And what this data table actually shows you is there are 3 different columns. There's the year on the left hand, the annual mean in the middle, and then the 5-year mean on the right. What I want you to do, completely ignore the right column. We're not going to do anything with the 5-year mean. We're just going to focus on the year and the annual mean. So let me tell you what you're actually looking at here. These are what are called anomalies. Who can tell me, take a quick guess, what is an anomaly?
Something that's not usual, abnormal.
Something that's abnormal. Something that's abnormal. The way that we actually define an anomaly, mathematically speaking, is it is a difference from average. So an anomaly is a difference from average. So what that means, let's say I were to give a test and the average was an 80. An anomaly would be anything that wasn't an 80, any score that wasn't an 80. So let's say you got an 86. That would be a 6% positive anomaly, meaning that your score was 6% higher than normal. And then if somebody were to get a 75, that would be a 5% negative anomaly. That'd be 5% below average, 5% below normal. So that's what these numbers actually represent. These are anomalies compared to the 1951 to 1980 average. So these are the anomalies compared to that average. And so what I want you to do here is I'm going to ask you a few questions. The first one is, what is the biggest anomaly, the biggest positive anomaly? And so what you'll do is you'll peruse this thing really quickly and identify where the biggest number is. Now, if you actually want to know how to do this in a slightly easier way, one thing you can actually do is copy this table, paste it into an Excel spreadsheet, and then using the sort function, you can actually sort out the largest number on the top and the smallest number on the bottom. So that's one way that you can do it. And if you do that, that's totally fine. If you do that, that's totally fine. The other way is just to simply look through and look for where the biggest number is. I'll give you a hint, it's going to be close to the bottom of the table, close to the most recent years. And then there are a few other questions based off of that. There is one other thing that I have you do here, though. The other thing that I have you do here is I actually have you, these numbers are given to you in Celsius. The other thing I have you do is actually convert the Celsius value to Fahrenheit. Let me briefly show you how to do that. And I'll pick a number and it can be our example. So I'm going to pick the 2012 anomaly of 0.62. So this is in Celsius. So that's in Celsius. If I wanted to convert that to Fahrenheit, all I would do is I would take my Celsius number and I would multiply it by 1.8. I would multiply it by 1.8. And the reason why is because for every degree Celsius, there are 1.8 degrees Fahrenheit. So 0.62 multiplied using my cell phone calculator again, 0.62 multiplied by 1.8 gives me a value of 1.116. And again, if you just round this up to the nearest 2 decimal points, that would be 1.12 degrees Fahrenheit. Now, really quickly though, if somebody has ever taught you how to calculate, how to convert Celsius to Fahrenheit, there's an extra step that they may have taught you how to do. Do we have to change Celsius to Fahrenheit for A, B, C, D? Are you talking about for each one of those questions? There's just one question there where you have to convert to Fahrenheit. So there's only one question where you have to do it. And that would be question D. So you only have to do it for question D. So one of the things that, if you've ever been taught how to convert Celsius to Fahrenheit before, one of the things that people probably taught you how to do, or taught you to do, was also add 32. Here's why you're not doing that here. The reason why you're not doing that here, when you add 32, what you're actually shifting, what you're doing is you're actually shifting where 0 Fahrenheit is, or where 0 Celsius is, sorry, where 0 Celsius is. 0 degrees Celsius is 32 degrees Fahrenheit on the temperature scale. But the thing is, we're not actually calculating temperatures like an absolute temperature. Instead, we're calculating what's called an increment of temperature. So how much has a temperature changed? There you leave the 32 out, because otherwise you're going to get a really weird number. Otherwise, you're going to get a number that looks more like 33.12 degrees Fahrenheit. And that actually won't make sense. I could go more into why it wouldn't make sense, but just trust me, it wouldn't make sense. So you're just taking the number, multiplying by 1.8 to get Fahrenheit. You're not adding 32 because we're only doing increments here. We're not doing, like, you don't have to shift the scale. You're just doing an increment. So that is how to do that. So that's for question 2. And then finally, really quickly, for question 4, let me switch over. For question 4, I've given you a graph. Unfortunately, there's no data table for this. I'm sorry about that, but you probably won't need it anyway. And what I'm asking for here is what 2 years have had the highest sea ice extent and what was their value? And then what 2 years had the lowest and what was their value? By value, here's what I mean. So let me just pick a random number. In my morning class, I picked 1993, so I'm going to pick a different one now. Let's do 2008. So this point right here represents 2008. So that point right there represents 2008. So for 2008, the value is, and you can approximate, you don't have to be perfect on this. The value here is approximately 4.7 million square kilometers. So all I want you to do is give me the 2 highest ones and what their values are, and then the 2 lowest ones and what their values are. So that's all that I want you to do there. The other 2 questions, question 5 is a very open-ended question. And then question 3, you can actually just Google it and you'll find out what it was. And I'll give you a hint. We actually talked about it in the last class session. We actually talked about why that cooling occurred in 1992 in the last class session. So if you don't remember, you can look at the notes from the last class session and that will tell you. So that's all for homework 1. Are there any other questions I can answer about it real quick?
Where can I find this homework?
So if you go to our homepage, over here on the coming up section of the homepage, click on that and it'll take you right there.
Okay, thank you.
Absolutely. It's also under the week 2 module. So where it says homework 1 right there. So it's also right there. Alrighty. Are there any other questions I can answer right now? Do you need to answer those in full sentences? Yes, please. Any other questions I can answer real quick?
One more time, do we change? We change from Celsius to Fahrenheit, right?
Yes.
Okay.
And to do that, you just multiply by 1.8. So whatever number you have in Celsius to convert to Fahrenheit, multiply by 1.8. Alrighty. If you have any other questions, please don't hesitate to send me an email, or you can hang around at the end of class and ask, or you can ask on Thursday. But I hope that this helped with that homework assignment. Hope that this demystified anything that may have been a little bit more tricky than intended. And hopefully it's not too bad. It's not meant to be too bad. So, all right. So with that said, let's chit chat about what we're going to be talking about today. So today we're going to be talking about how we look into the past. So I've got you for like 35 more minutes. I'm going to talk about how we look into the past. And this is really important. And this is really important because the fact of the matter is that we only have recorded temperature data back to 1880. So we only have about 140 years of temperature data. Now that's a lot of data. If you're like me, that's boom, lots of data. But believe it or not, the reality is that's actually not a whole lot of data when you're talking about an Earth that is 4.5 billion years old and a galaxy that is over 14 billion years old. A universe that is over 14 billion years old, or almost 14 billion years old. So, we only have 140 years of data. So the reality is that in order to really determine if what we're experiencing now is something that we should really be afraid of, should be really alarmed with, something that we should really be concerned about, we need more data. We need more information. We need more information. And the information that we need is we need to know, how has our past climate looked like? How has climate looked like prior to 1880? So just to give a little bit of context, I mean, this is what we talked about last week. We had talked about the fact that according to the IPCC, Earth's global average temperature has jumped since 1880 by almost a full degree Celsius. By almost a full degree Celsius since 1880. Now that wouldn't seem like that's that big of a deal if this is just a normal part of climate, like if this is just what normally happens. But we need to know, is this what normally happens? Is this business as usual? Or is there something very unusual about what's been happening recently? And the only way that we can do that is we have to look further in the past. We have to look back further. And just this graphic right here that I'm showing you, I know it's a graph with a bunch of jagged lines and stuff like that, but let me actually explain what's going on here. So this blue line right here represents what we believe, based on reconstructions, were the global average temperatures compared to the 1961 to 1990 average. What global average temperatures were like and how they've changed over the past roughly 1,000 years. And if you notice, for most of that time, it's been a little bit of jaggedness, but for most of that time, the temperatures have actually kind of remained right around the same area. There's a little bit of a dip around 1500. This is actually what we refer to as the Little Ice Age. But otherwise, for the most part, temperatures have actually remained relatively steady until we've gotten to these last 2 centuries. And then if you notice, temperatures have taken a pretty noticeable jump upwards. They've taken a pretty noticeable jump upwards. But how do we know? So we know all of this. We know this because we have direct observations. But how do we know all of this? All of the stuff prior to when we had direct observations? Well, the good news is, even though we don't have direct temperature measurements, we do have other ways to actually determine what the temperature was like during those times. These are what are called proxies. So a proxy is just a fancy word for a representative of something. It's like a substitute. So let's say I got sick, I couldn't teach class, but there was too much stuff to cover, I could not cancel a class. But I can't teach it either because I'm sick. I could have somebody come in and substitute for me. That person would be my proxy. That person would be my proxy. They would be my substitute. They would be my representative. They would come in using the authority that I have, using all the stuff that I have, and they would represent me. Well, even though we don't have direct temperature measurements prior to 1880, we do have a set of proxies, things that we can actually use to represent temperature. Now, the good news is we actually have a lot of verification for these proxies. We know that they're legit. And the reason why we know that they're legit is because we can compare what they are saying now to what current readings are. So we can calibrate them using current readings. So we can look at what is going on now. We can look at what is going on now, and we can compare it to what the proxy says is going on now. And that allows us to calibrate, to say, okay, well, there's a certain amount of this gas in the snow, and this is what the current temperature is. So we can say that when the temperature is this, there would be this much of this gas in the snow. And that'll make more sense in a few minutes. Now, there are three key proxies in climatology. The first one, that whole gas and snow thing I talked about, ice cores. The second one, tree rings. And the third one, sediment samples. So these are the three things, these are the three big things that we actually use to represent past climate shifts. So ice cores, tree rings, and sediment samples. Okay, so first let's talk about ice cores. So suppose you're in Antarctica. In much of Antarctica, even in the warmer world of climate change, in much of Antarctica, the temperature never rises above freezing. It never rises above freezing. Here's what that means. That means that all of that snow that's there is going to stay there. That snow is not going to go away. It's not going to disappear. It's going to stay there. It's never going to melt. What's interesting, though, is that this snow was made in the atmosphere. And so when the snow was made, embedded in it are little bubbles of atmospheric air, little gas bubbles that actually contain the composition of our atmosphere. Things like nitrogen, oxygen, argon, carbon dioxide, methane, different isotopes of oxygen. All these little things are actually embedded in that snow. And then that snow drifts down and hits the surface of the earth. But it never melts because in this particular part of the world, the temperature never rises above freezing. Then the next year comes, and guess what? The next year, more snow falls on top of that. And then the next year, more snow on top of that. And then the next year, more snow on top of that. And then more snow on top of that. More snow on top of that. And so on and so forth. And so what we get is we end up getting these layers of snow, each one roughly representing a year. So here's this year's snow on top of last year's snow, on top of the year before that, on top of the year before that. And so what we end up getting is all the snow hardens into basically solid ice. And what we basically end up getting is trapped in these layers of ice are bubbles of ancient atmospheric air. So here's what we do. In order to actually figure out, okay, how much carbon dioxide was in the air 2,000 years ago, or 5,000 years ago, or 10,000 years ago, what we can actually do is go to one of these places out in the middle of Antarctica where it doesn't melt, And we can, using a drill, we can actually bore out these long tubes of ice, what are called ice cores. And what I have right here is, this is Vostok, Antarctica. There is a former Soviet research base there. It's now a Russian research base, but it's used internationally. So it's used by Russians, Americans, French, British, other scientists use this site. So there's a lot of international cooperation here, as seen in this picture. So this guy back here does not seem happy. And what all of these people are holding, these long tubes, these are the ice cores. These are the ice cores. And so they're holding on to these long ice cores. And embedded in those ice cores, you can almost kind of see them, even are little bubbles of air. And we can extract that air, and then we can run analysis on it to find out how much carbon dioxide was present during that time. What oxygen isotopes were present during that time. And each of those things can actually give us an accurate reconstruction of past climate, which, if you ask me, is really cool. It gets better though. And I'll talk about how it gets better in a few minutes. So we do this using ice cores, both in Greenland and in Antarctica, as well as other parts of the world. So we use this. This is one way that we reconstruct past climate. Now, that being said, okay, that's kind of cool because you're in these areas where there's all this ice and stuff like that. That actually gives us a really good picture of past climate. But that's not the only thing that we can do. You see, this same principle, how snowfall has stuff embedded in it that we can then look at to determine past climate, the same is also true for sediments. Right now, as I speak, and as you are all listening, all around the world, there are mountainsides being rained on. And when rain hits those mountainsides, it actually erodes very, very slightly, but it erodes a little bit of sediment from the mountainside. This sediment then rolls downhill into lakes, rivers, streams, eventually out to the ocean, where it then wafts its way down to the ocean floor. And so you get all of this seafloor sediment that develops. And just like with snow falling every year, that seafloor sediment, once it reaches the seafloor, it's kind of just stuck there. And then the next year, or the next day, or the next moment, more sediment comes on top of it. And then the next year, more on top of that. And then more on top of that. And then more on top of that. And so what we end up getting, just like past climate is locked in these ice cores, we also get the same thing with seafloor sediment. And so in addition to research bases like the Vostok Antarctica Research Base, we also have ships that actually go around the world and actually take long tubes of sediment from the ocean floor, dig it up, and analyze it just like we do with the ice core. So what I have here, I warn you, the music is kind of corny. But what I have here is a short video that shows you how this is done. So this is one ship. This is actually one of the most famous seafloor sediment drilling ships. This is called the JOIDES Resolution. And what it does is it goes all around the world, and it actually goes on expeditions where they go to a place, they launch this drill, they drill up a sediment core, and then they analyze it. So this video just kind of shows how that happens. So again, please forgive the corny music.
The main purpose of the JOIDES resolution is to drill into the ocean floor and bring up sediment cores for scientists to study. These sediment cores can give us a lot of information about the Earth. Many pieces of pipe are put together under the derrick on the rig floor into what is called a drill string. The crew attaches a drill bit to the end of the drill string and lowers the entire thing through an opening in the bottom of the ship called the moon pool.
So there goes the drill.
Once the drill string reaches the ocean floor, coring begins. A long cylinder of plastic called a core barrel is lowered through the drill string, and the sediment cores are collected inside it as the drill string rotates. The core barrel is then pulled up to the ship through the drill pipe and onto the rig floor, where the technicians and crew collect it and begin to prepare it to be examined by the scientists.
So basically what's happening there is the JOIDES resolution, as it's going out, it's doing this. It's actually going out and it's drilling out these long sediment cores. And then what we can do once these sediment cores have been drilled, they've been pulled up, they've been prepared for scientists to study them, scientists can actually then take a look at these cores and extract things from them, including things such as fossils, including what the mud or the sediment is actually made up of, including any sudden changes in the chemical composition, which could actually indicate a change in the environment, which could then indicate, hey, something really big just happened here. Something really big just happened here. And right now, even as we speak, the JOIDES resolution is out there doing this research. Even during COVID, even during the pandemic, this ship has been out there, obviously using social distancing protocols, and people had to quarantine for 2 weeks before they can get on the ship. And but even right now, as we speak, they're out there collecting sediment cores from different places around the world that could then be used to investigate past climate. And here's basically what they pull up. These are just long tubes. They're not very thick. They're not very wide. They're not very big. They're just really long. But this is what you see. Basically just these layers of sediment that have been sitting at the ocean floor for millennia. And if you notice, the ocean sediment in some cases almost takes on a stripe-like structure to it. Kind of like here, 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 and here. Now, what does that actually mean? Well, when you see these different stripes, what that actually means is that over time, the chemical makeup, what has actually made up the sediment, may have changed over time. If it's more iron-based, you may actually see more of a rust color, because when iron oxidizes, it kind of creates like this rust, reddish brown color. And other times, maybe there's a big volcanic eruption and you can actually see volcanic ash changing the color of the sediment. And so in that case, the sediment may take a darker gray color. So this is actually how sediment cores work. Believe it or not, tree rings actually work very much the same way. What scientists actually do in order to extract information from trees, because we actually do that as well, we look at tree rings, instead of actually going out to a tree, cutting the whole thing off, and then counting the rings, what scientists can actually do is, using a tiny little drill, they can actually drill and bore a core of tree ring. So instead of actually having to like chop down the whole tree and cut off a core or cut off a tree ring and stuff like that, you can actually just bore just a little tube and then pull that out and look at the rings. So you can do that and minimize the damage done to the tree. And so each one of these things we can actually investigate past climate without really causing a lot of damage to the ocean floor, causing a lot of damage to things. So there's actually some pretty good things about this sort of approach. All right, now that being said, let's say the JOIDIS resolution went and it got a long sediment core. Or our friends at the Vostok Research Base in Antarctica went out and got a long ice core. Or a scientist named Dr. Dendro, and I'll explain where that name comes from next time, went out and got a little core of tree from a tree. What do we do with that now? Well, what we do with that is a two-part process. In order to figure out what it's telling us, we have to do two things to it. The first thing we have to do is we have to date it. We have to date it. And then the second thing is we have to analyze it. So we date it and then we analyze it. So what I'm going to do is I'm going to talk briefly right now about dating it. All right. So you take your sample, you find a nice restaurant, you get a reservation, you take it, you buy it a glass of wine, you buy it a nice steak dinner, and you sit down and you talk to it for a couple of hours. Obviously, that's not what I mean when I say dating a sample. You're not actually taking it out on a date. Instead, what you're doing is you're actually figuring out when that sample represents. What period does that sample represent? What year? What date? What era that sample represents? Now, here's the good thing. Mother Nature actually gives us a lot of hints that we can use to date something, that we can use to determine what time this thing represents. So Mother Nature actually does a lot of our work for us. And all we have to do is listen to Mother Nature. Here's what I mean. So first off, why do we even care about this? Well, I don't know about you. I want to know when the last time Yellowstone erupted. Why? Because that can give us a lot of insight as to when it might happen again. I don't know about all of you. If the Yellowstone volcano was to erupt tomorrow, I'd want to know. Well, even though we can't directly predict that it's going to erupt tomorrow, we might want to be able to tell, when did it happen last time? So we know if we're due or not. How do we know when the dinosaurs died? They died about 66 million years ago. But how do we know that? How do we know that a previous biological or geological era ended and a new one began? Well, we do that by dating. We do that by dating. And there are actually two ways that we can date something. The first one is using what's called the principle of superposition. And the second one is using radiometric dating. And so what I'm going to do, I've got about 10 minutes left. I can actually go over each one of these briefly with you all. And then next time we'll talk about what this stuff actually has to say, what these samples have to say, what this data actually shows us. And then we'll be able to reconstruct our previous climate. So here we go. First, the principle of superposition. It sounds like a pretty complex term, but it's actually a pretty simple concept. The concept is that if I have a layer of something, or if I have something that's layered, the newest stuff is going to be at the top. And that kind of makes sense. If it snows outside, the most recent snow is going to be at the very top. And the further down into the layer you go, the older the snow gets. Well, the same is true with sediment cores and with ice cores. The newest stuff is going to be at the top. And then as you progress your way down, it gets older and older and older and older. So the newest layer is on the top, and then each successive layer is older and older and older. The principle of superposition is actually a very valuable, very useful thing, because we can then use that to actually show us how old something is. We know the youngest stuff is at the top, and then the older stuff is each successive layer below. Now, here's the cool thing. With sediment samples, it's a little bit more complex. But with ice cores, Mother Nature actually gives us a calling card. Here's why. And tree rings work and by the way, tree rings work the same way. The exterior most layer is the newest one. That is the most recent growth. So tree rings work the same way. But let's talk about ice really quickly, because what actually happens with ice is really cool, and I don't just mean temperature-wise. So, believe it or not, Antarctica and the northern part of the northern Arctic, believe it or not, they get the bulk of their snowfall in summertime, not in wintertime. They actually get it in summertime. I'll explain why later in this course, but basically, when weather is warmer, that means that there's more evaporation. More evaporation means more clouds mean more precipitation. So anyway, with that said, summertime is when areas such as Vostok, Antarctica get their snow. Winters are usually very, very dry. So here's what happens. Every summer, Vostok, Antarctica gets snow. Then winter comes. Winter, as I mentioned, is very, very dry. However, during the wintertime, there's no new snow falling. But there's still dust around. Even in very, very, very clean air, there's all kinds of little particulate matter, whether it's bacteria, smoke from fires thousands of miles away, ash from volcanic eruptions. There's all kinds of little stuff in the air. And all that stuff in the air settles down onto the very, very top of the snow. And that darkens it just a little bit. And so basically what happens is every summer, snow falls. Every winter, the very top of that snow gets darkened. Then the next year, more snow falls. Then the top gets darkened again. Then more snow falls, and then the top gets darkened again. More snow, more darkening. And so what you end up getting is this really cool feature where summers end up being represented by these bright looking stripes in the ice, and winters end up being represented by darker bands in the ice. And so what you end up getting is this striped feature of light stripe, dark stripe, light stripe, dark stripe, light stripe, dark stripe. Every light stripe represents a summer. The next dark stripe represents a winter. Then the next one a summer. Then the next one a winter. And so each pair of light and dark represents a year. There was summer, and then there was winter. That's a year. Then the next summer and the next winter. That's the next year. And so what we can actually do, combining that with the principle of superposition, when we look at these ice cores, what we can actually tell is, okay, that first layer of light and dark, that is the most recent year. The second layer of light and dark, that was last year. The third layer is the year before that. Then the fourth is the year before that, the year before that. We can literally count the years. I mean, that's Mother Nature leaving us a date stamp. It's almost like Mother Nature's telling us, this was 2020, this was 2019. That's fantastic if you ask me. That's so cool. And then the same thing happens with tree rings. Again, like I said, the most recent one is the outermost one. Then the next one is last year, then the next one's the year before. So that's superposition. And that's Mother Nature leaving us a little bit of dating information. But that's not enough. If you take a look at sediment samples and other things, they don't necessarily have, as I mean, almost literally black and white, a way of figuring out what year it represents. So you need something else. Well, guess what? Mother Nature still has us taken care of. The reason why, isotopes. How many of you have ever heard of an isotope before? And I'm not talking about the Albuquerque isotopes. Springfield's team after they moved to Albuquerque. There is an actual Albuquerque isotopes team. I know I was in Albuquerque a few weeks ago. But an isotope is basically a variation of an atom. So atoms usually have a set number of protons and a set number of these things called neutrons. Well, an isotope has a different number of neutrons than protons. Isotopes can either be really, really stable, meaning that they always stay the same, or they could be really, really unstable. And by unstable, I mean that they decay, they fall apart. Well, there are some isotopes that naturally occur on the surface of the Earth and naturally occur when exposed to sunlight that exist. Case in point, carbon-14. Carbon-14 is produced when sunlight strikes the atmosphere. So sunlight strikes the atmosphere, carbon-14 is created. All of us, either from the food we eat or from the air we breathe, we are consuming that carbon-14. And so all of us right now, we all have a little bit of carbon-14 in our bodies. And then we die. I know. Then we die. When we die, that carbon-14 stays locked in our bodies. However, because we're dead, we're no longer consuming any more carbon-14. So the amount of carbon-14 in our bodies doesn't increase. However, the carbon-14 that's already in our bodies begins to decay. And the cool thing is that it actually decays at a set rate. Of all the carbon-14 we have, over a period of 5,730 years, half of it decays. So I die, I have a set amount of carbon-14 in my body. Over that 5730 year time period, half of that carbon-14 decays and leaves my body. It becomes other things. And so now I only have half of the remaining carbon-14 in my body. Then in the next 5730 years, what's left, half of it decays. Then in the next 5730, another half decays, and then another half decays. And so what we can actually do is we can determine, based on how much carbon-14 is in something compared to how much it would have if it was still alive, we can determine something's age. We can determine something's age. And so this is a way that we can look back as well using radiometric carbon dating. Now it's worth noting, and this will be the last thing I say before I wrap up today, it's worth noting that carbon-14 isn't the only element that we can do this with. There are other elements that have much longer half-lives that can allow us to actually date something back tens of thousands of years, hundreds of thousands of years, even millions of years. And so we can actually, with a sample of something, we can actually date a sample of something to a pretty accurate degree. Now, that doesn't mean we can't date it back to, okay, September 7th, 2014. We can't give it an exact date, but we can at least estimate around what time this sample represents. And it's because of that that we know the dinosaurs died roughly 66 million years ago, because the last dinosaur fossils that we saw using radiometric dating were about 66 million years ago, about 66 million years old. All right, now with that said, that's pretty much it for today. What I'm going to talk about next time is what are these samples actually telling us? How can we take these to reconstruct climate? So we're going to talk about that next time. So that's everything for today. If you have any questions, comments, concerns, threats, anything else, I can hang around for a few minutes. Otherwise, I will see you all on Thursday. So long.
Professor.
Have a great day, everybody.
The multiple choices on Thursday, right?
Let's say it again.
The multiple choices on Thursday, and the
Yes.
homework is due before class, right?
Wait, say it again.
The homework is due before class starts, right?
It's due by 11:59
Okay.
p.m. that night.
Okay, makes sense. All
All
right.
right. Yep.
Wait, what did he mention? There was a multiple choice.
Oh, our first quiz is on Thursday.
Okay, and then how do you like recommend us preparing for the quiz?
So there is a study guide that I actually posted on Canvas.
Okay, thank you. And
Yep.
then
All right, for sure.
it was just for the homework, it was just accuracy, right?
Yes.
Okay, and then like how lenient is that? Like you just want us to do like our best, or like does it matter how much we get right?
I'm a little unclear as to what your question is. I do grade it based on accuracy.
Okay,
I try not to be like super strict with it either.
okay,
All right.
thank you.
All right. All righty. And that's that.